My blabbering does double duty. So reminder to you all. So quiz 1 was due this last Saturday. Sent out, it's a thing. So hopefully got all that done. Woohoo. And then reminder to you all, 1D kinematics, instead of doing this coming Saturday, will actually be due. One day this will sync. There it is. It was going to be due this Saturday, but I told you all, hey, we're not going to actually finish 1D kinematics till today. So quiz 2 is due on the 29th. Send out an announcement so it's in writing, so you can reference that if you're ever confused. Or I've also updated the due date. Now, do note that 2D kinematics currently is due that Saturday. That's still the plan. The good news is 1D kinematics and 2D kinematics, they're the same thing. Like 2D kinematics is just doing 1D kinematics twice. That's all it is. So all your all's practice towards doing kinematics, it's the same thing. All you have to know is you have to split up the X and Y. And if I find that it doesn't seem like enough time, I could extend that, but we'll see. I'm not currently planning on doing that because right after that, we're getting into forces, and I just want people. The reason for the deadlines as they are is when I think they should be kind of based on timing and all that kind of stuff, when I think is a reasonable time by which you should have a decent understanding of it. I do not expect by the time the quiz is due for everyone to be an expert at it. You've only been working on these things for like a week or two. Like, that's just not how expertise happens. But the name of the game when it comes to this class is by the end of my class, if you're decent at it, that's good. Being an expert in something takes many more hours than can be achieved in a single class. But you can get a solid understanding within a single class. And then if it's something you're interested in, you can spend the hours to get to it. I forget. There's like something like expertise is like 10,000 hours or 1,000 hours. I forget the number. But there's a thing with it. All right. So I'll always recap the last. So that's logistics. I think that's kind of it there. Lab grades. So your TA is putting in those grades. He did mention to me that there is some subset of students that maybe weren't in a group that maybe should have been. So note that, are all those grades kind of in it? The ones that you could do, are they done?
Not yet. I was going to do them this afternoon.
Okay. So by the end of today, sometime by tomorrow, just make certain you have a lab grade. If you think you should have a lab grade and you don't, ping me, but you're also going to have to let me know who in your group submitted the lab report, because I have to be able to check that. That's the backup basically for these things. If you miss signing up for the group or things like that, that's what's going to happen. Yeah. They should do that already. They have due date. They don't. I was like, they should. They have to-do dates. I'll make a note of it. They should. I mean, my assumption was if I put a due date on something that it pops up in that. But I'll look into it. Check quizzes to-do list. Yeah, that was always my running assumption with that. As long as something had a due date, it popped up in the to-do list because there's no like box I'm familiar with that says put this and that. But I'll look into it. Maybe there is something I missed, or it should be an assignment. Anything I make that's graded kind of immediate. Yeah, it's definitely in the assignments category. Well, it's in the assignments tab in a group category called quizzes, but so it should be in there. But I'll look into it. I'm not sure why that is. That stuff is convenient to have, and I just assumed that it would default to doing that with a due date. But in this case, I guess it's not. All right. Last class, we got through most of kinematics. So I'll always try to do a recap of the last class just to help us. This looks disgusting. Let's look at this one instead. So last class, we got to these equations, and then we practiced them. That was the name of the game last class. And it all came down to what's given, what are you solving for, find the equation that has those things, put stuff in and solve. Nice, straightforward. If it's seeming complicated now, I can almost guarantee you if you just practice some of these problems, it will settle. And as long as you're going through those steps. So even though this is the most, like any concept moving forward, I won't give you this many equations at one go. So this can be like intimidating equation-wise. but it is one of the most straightforward parts of this class because it very much is givens, missing, find the equation, do it. Future topics are going to have some different kind of in-between steps you're going to have to do. So, anywho, there's those. We practiced them. It was a good time. Did some things. Woohoo. They're all worked out here. Gave you all this problem, which said that, hey, you know, it's not always going to be this trivial of just find that. Sometimes you have to do a little clever thing. And the clever thing in this case was they said their final positions were the same. So we said, hey, a cool strategy you can actually do is you can take these equations and set them equal to each other. So like you can take an entire equation, and if that entire equation equals the final position, I can take this for one person and then set it equal and then write the whole thing again for someone else. That's a thing you can do. You can do the same thing with final velocity. If you know two people have the same final velocity at some point and you say, I want to find the time, you can just take this equation up here and you can set them equal to each other. You can say V naught of person 1 plus A1 times time equals V naught of person 2 plus A2 times time. This is the thing you're allowed to do. They equal each other, then they equal each other. And that whole equation equals that. So there you go. So that's the reason for that problem, is to show you that that's an option. That is a thing that you can do. A lot of people don't realize that. There's a lot of problems in physics that have these little, I'm going to call them tricks, and they're not like a trick where it's like, oh, I'm trying to confuse you or things like that. They're just things you don't realize you can do until you see a problem like it. And once you see a problem like it, then hopefully you can do other problems similar to it and all that kind of jazz. If I told you the accelerations were the same, you could take one of these equations, solve for acceleration, and do the same thing. Set them equal to each other. And it's a good time. All right, great. So that was last class. Did some things. Lots of fun. The last thing I didn't get to is going to be very important for 2D motion, but it's just important in general. We live on Earth. And on Earth, there is one thing that makes things, there's a really common thing that makes things move, and it's gravity. So gravity is what we're going to be spending a good amount of time on today, specifically for 1D and 2D. So this is the rule. If something's in the air, it experiences gravity. If something's on Earth, it experiences gravity. I should just say that, but I made it a little bit more clear here. If you have an object that's in the air, you're going to have to account for gravity. Just like that should be somewhere in your mind. That's a little flag. If something's in the air, gravity should pop up in your head. We're going to assume every problem is on Earth unless stated otherwise. That's a good assumption to make. It's one that you've been making this entire time. But just to clarify that. And if something is on Earth and it falls through, it's fallen, or whatever, it's in the air. If I let go of this baseball, it's going to experience an acceleration of negative 9.8 meters per second squared. That is true. Assuming no air resistance. That is, it says that assuming no other forces acting on it. This is going to be an assumption in every single problem we do moving forward. Assume no air resistance. It'll very often say it in the problem. If it doesn't say it, assume it. Basically, if there's air resistance, I will tell you. That's more so. Assume no air resistance. If there is air resistance, I will tell you, and you're not going to deal with it when it comes to kinematics because my goodness, is it gross. At some point, I'll show you the equation for it. There is an equation to calculate the force due to air resistance, and it depends upon the velocity of your object squared. It depends upon the surface area of your object. It depends upon the shape of your object, and it depends upon the viscosity of the fluid that it goes through. It's a complex calculation, mainly because as you go faster, the force gets larger. As the force gets larger, it slows you down. As you slow down, the force changes, and it's a feedback loop where the force affects whatever. Future things. For now, assume no air resistance, like that, just in general. Now, also notice that if you're traveling downwards, we're going to see this. If you're traveling downwards, I'm actually going to change this thing, and I'm actually going to make it a little bit bigger because I think this is a little too small. This is something we're going to see in a problem. If you're falling, your change in y is negative. We're going to see why this is when we do some problems. It's going to be really easy for me to prove that to you all. I just got to make up an example, and we'll do that, but I'm mentioning it now. These are just kind of the main things So, yeah. Now it's going to be kind of applying it in various situations. A equals negative 9.8 if you're in the air. This is a given. If something is in the air, I don't care if it's on its way up. I don't care if it's on its way down. I don't care if it's going sideways. I don't care which way it's going. In the vertical direction, if there's no rockets attached to it or motors or anything like that, if it is just, look, this baseball, after it leaves my hand, it's negative 9. The acceleration is negative 9.8 downwards at every point in its flight. On the way up, acceleration is negative 9.8. At the highest point, negative 9.8. On the way down, negative 9.8. Everywhere after it's left my hand and before it touches my hand again. When it's in the air. So that's the major theme today. If you can understand that, things will be smooth. Don't worry about this one. That's just extra practice. I'm going to check that one up here because it doesn't have to do with gravity. All right. Everyone's favorite question. The feather and the wrench. Anyone this is just always the question that gets asked regarding free fall. A wrench and a feather are both dropped at the same time. Which will hit the ground first? Assume no air resistance. Wrench, feather, same time. Yeah, it feels like a staple to me. If a physics class doesn't have this question, something feels off. Yeah, that's the next. Yeah, I don't know if I put it in here, but I will pull it up after this question. Yeah. It's really high quality video quality because it was in the 70s on the moon.
Yeah, it doesn't say.
Yeah.
Should we assume that they're dropped from the same?
Yes, yeah. Assume they're dropped at the same height as well. That's very, very important. Makes a big difference if one's dropped from a mile high and the other's a meter high. All right, we're going to go a few more moments, give you all like 10, 20 more seconds. And then they did this experiment. I'll show you a video of this experiment. And we'll find out the answer. All right, in 5, 4, 3, 2, 1. So I'm not going to show you I'm not going to tell you the answer. Again, they did an experiment. So this is going to be really weird where I play a YouTube video to show you. So I'm streaming a YouTube video and I'm going to play a YouTube video. I don't know how YouTube feels about that. All right, NASA, I think it was Falcon. Well, just wrench versus feather. Yeah, I believe you're correct as well. So there you go. I don't know which one's better. This one has more views. I think this is the one I picked, but they're all the same. So great. We're going to go to a place.
We copied both solar wind and penetrometer.
Is the video quality terrible? Yes, because it was in the 70s on the moon. Like, there's a lot of constraints there. So, as it moves, it's a little bit easier.
Picture there. I've got beautiful picture, Dave.
Beautiful picture. So good. I mean, he's on the moon.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that? Yeah, so this is the classic experiment. Like, this is such a classic in a physics class to mention this. We are so used to air resistance. Like, you live in a world with air. You have to breathe it to survive. You all don't really exist in places without air. In physics, we have to start simple. We're not going to bring air resistance into things because that's incredibly complex. And it turns out ignoring air resistance actually gets you a pretty good understanding of a lot of things. Air resistance really only matters for things with a big surface area or they start to go fast A lot of things like a ball, baseball going through the air, you can get a sense of what it's going to do. You can get a pretty accurate answer by just ignoring air resistance. That's what you're going to do on Thursday on the lab. So, to that end, on the moon, obviously it's not Earth. There's no air, so great, it's removed. The gravity is weaker. It's not negative 9.8, but you get the same results. All things. So this is going to be a really important question that I end up almost putting on every single test in some fashion. It's an interesting little thing. It shows up because there's so many ways to prove this. When we get to energy, you can prove this with energy. When we do kinematics, it is just kind of a statement that gravity affects all things the same because they all have the same acceleration. And so it's my mitochondria is the powerhouse of the cell. It's one of those things for me. That all things get affected by gravity the exact same. And as we get into forces, maybe I'll make up a problem to show you why things fall slower. But this is actually really easy to prove, that gravity affects all things the same, that it doesn't depend upon the mass. You know, I got two pieces of paper. They have the same mass. If I just crumple one up, it still has the same mass, didn't change its mass, and it falls to the ground quicker. What's the only thing different about them? The surface area, air resistance hits them more. Ta-da, air resistance makes things go slower. Super, super easy explanation that you can do with like any kid at any age. Hey, these things are the same thing. I just crumpled this up. What changed? This one's smaller. Air is the reason things fall slower, and that's the only reason. Again, it gets, okay, there's like forces and stuff like that when we do air resistance, but if something's in the air, I don't care what it is, a person, a baseball, a boat, I don't care what's in the air, it's experiencing an acceleration of negative 9.8, assuming there's no rockets attached to it. So, this is a classic problem. There's only a single number written in this whole thing, and yet there is 3 givens in this problem. Technically 4. 4 givens. So my challenge to you all is see if you can find the 4 givens. You know, you can try to solve the whole problem if you want. I'll quickly solve it on my calculator and put the answer here. So there you go. The answer's there if you want to check your work. But yeah, for now, just try to find the givens. There's 4 of them.
So you're trying to find time. Wouldn't the acceleration be the same? Oh, it's negative 9.8 because gravity is in the air. It's the acceleration.
This one, what I'll show you all. What height does it start at? What's its initial? Its initial 3 with its final 0. So changes to final minus
Maybe he's
initial.
saying like
0
delta
minus
x
3
and delta x. Yeah.
And you don't put the negative, it will mess
Mhm.
up. Either mess up your sign or mess up your answer entirely. So yeah, to be fair, that delta y on this. So depending on your perspective, it might be only 3 variables if you collapse 2 of them together, but at least 3.
Yeah.
Be careful about positive or negative.
Oh yeah, it's finally.
Acceleration is not displacement.
Yeah.
All right. So y'all tell me real quick what's some of the givens. I'm just going to do step 1 and then I'll leave the rest for y'all. Initial or final?
You have an initial.
Oh, that's a good point. Yeah, which one's 0? So it says it starts at rest, so the initial is 0. Now, something really common that people do is they say it hits the ground and it stops. That is true, but in this case, we never, when it says hit the ground, we actually consider right before it hits the ground. This is a super important thing. As it's falling is one problem. As it's hitting the ground is an entirely different problem. Because when it's hitting the ground is pushing on it. And that's its own problem entirely. So we always do right before it hits the ground. If you notice my picture, there's a very tiny gap between the ground and the ball. So we actually don't know the final velocity. Because the final velocity is right before it hits the ground. We do not know that. But it's something I want to mention. It's a classic mistake is to say final is 0 because it hits the ground. Don't do that. That's because that's its own problem and an incredibly complex problem is when it hits the ground, what happens to it, all that jazz. But it's a really good point. All right, what else? What else is good enough? I need at least 2 more. What is the acceleration? Negative 9.8. I don't care which way this thing's going. I don't care if it's going up, down, left, right. And I'm even going to do this now. The acceleration in the y direction is negative 9.8. I'm going to start using that notation now to prepare us for 2D motion. Because you'll see when we get to 2D motion. Let's just leave it at that. All right. 1/2 more givens, depending on how you frame it.
What about this position at 3 meters?
Ooh, okay. Beginning or final? Beginning. And this is an important thing. Where do you all want to define your We always have to define a reference point. Where is 0 in this picture? Where do you all want 0 to be? The line, the ground, that's really common. It doesn't have to be. It doesn't have to be, but we're going to make that decision. It's pretty common. It's intuitive. In that case, if we say the ground is 0, then my initial, and notice I'm actually using y here instead of x. Again, this is preparing us for 2D motion. Everywhere you all saw x in an equation before, you could replace with a y. Every equation before that had an x could be a y or it could be a z. X, y, z, they all describe the same thing, just in different directions. So, y initial is 3. And we just decided that the ground is 0, and so it ends at the 0, and bam, there's your givens. And something I want to point out here is you might have put delta y, and that's totally valid. Remember, delta y is y final minus y initial. My y final is 0. My y initial is 3. That means your delta y is not a positive 3, but a negative 3. And this is what I mentioned before. If you're going down, delta is negative. And you can just choose initial and final and see that for yourself. If you're worried about forgetting that, just choose initial and final. Actually write those variables, do the math. Oh, look, it's negative. Works out great. All right, have fun with the rest of it. Answers up there. Work together.
I think it'd be that one because we don't have the V and T is the final delta V. So we don't have that. We don't have to use, we don't have to find the I don't think it's all super. He wants the time, like So I think we do
Now choose the equation. You always want to put what you're solving for because you'll never be able to choose an equation if you're not sure what variable you're looking for. And then you've got to find the equation that has all these things. And remember, everywhere there's an x.
That's not. I'm looking at this it would be x
Hello.
So I initially used acceleration is velocity by time, breaking down that equation like this, and it did not give me wrong answers. So I know this is not the right way to solve it.
Okay.
But I just wanted to understand why is it not the right way to solve it.
So
What did I do
displacement isn't just acceleration isn't just displacement divided by time. You can't just use the units. That's where you always want to reference what equation here did you use. That's where you want to pull your equation from.
wrong? Okay.
If you try to kind of like derive the equations, so what you ultimately were kind of trying to derive was this one, and what ends up is there's this half term, and you can only get that from calculus and things like that.
Okay.
So when choosing the equation, you always want to reference this.
Okay.
Yeah.
So don't go for the traditional.
Don't go from the units. Don't, like the units tell you what variable it is, but don't try to.
Then would I be using like acceleration as a displacement by
So acceleration is a.
A?
Yep, that's the variable.
Okay.
And
So
then
just never use this.
yeah, don't use that. Yeah, that's the units for it. Like match that. But yeah, you're gonna want to always refer when choosing an equation. Refer to this. If you try to derive them yourself, you could probably derive the first three, but the fourth one requires calculus to be able to derive yourself on the fly. Yep, that's it. What's 0 minus 3? And that's where you yeah. So the delta y. So the negatives cancel because otherwise that's actually technically you can't take the square root of a negative, but it gives you an imaginary number, which is meaningful in quantum mechanics. But so actually in physics, imaginary numbers do mean something, but not. A negative. Yep. So it's the same thing. It's gonna be when you take the square root. So which way is this thing moving at the bottom, up or down? So should the velocity be positive or negative? When you take the square root of something, remember both the positive and the negative answer. So for example, the square root of 64, there's two possible solutions, positive 8 and negative 8. And so you have to make that decision. And if you make the wrong decision, it can actually Yep. Negative time, we're not going to ever have a negative time. That means going backwards in time, which is not going to happen. How'd it go over here, y'all? The answer? Now you have one equation with one unknown. So you can solve it. Yep. Why would you do it? So it is possible to take this downwards with an initial Do we know the final velocity? So this one requires what is this going down? That's the process you use all right. So to start kind of working through this now, notice I copy and pasted the equation sheet from last time, and I replaced all the x's with y's. They represent the same thing. It's just whether you're horizontal or vertical. The equations work the same. They both measure where you're located. We just use y for vertical. We use x for horizontal, but they're basically the same. They're both measurements of where you're at. All right, what are we solving for, y'all? Just to continue the process. Time. And then we choose the equation that has what we have and has what we need. And it turns out that that's, and you know what? I'm purposely going to write it weird. So it's this one, xt equals x naught plus v naught t. Reminder to you all, this is the same thing as if this was this and this was this. They're the same thing. These two are, x and y's are interchangeable. They're not necessarily interchangeable. We use y for vertical and x for horizontal, but the equations are identical. It doesn't matter whether you're up, down, left, right. The kinematics equations are the same. You just replace all the x's with y's. Or if we got really spicy, we could do z's, and that'd be the third dimension, like in and out or something. Depends on how you define the z axis. So, purposely writing it, and I'll even put same as y of t equals y naught plus v naught t plus 1/2 at squared. And then step 4, you just plug it in. Remember, y of t is the same as y final. So 0 equals 3 plus 0 times t plus 1/2 times negative 9.8. If you do not put the negatives, it will bite you in the butt. It will mess up the answer. If you're lucky, it'll only change the sign. If you're unlucky, it'll actually change the answer entirely and get you the completely wrong answer. This acceleration, just reminder what it means. Negative means down. A negative acceleration means I'm speeding up downwards. Which way does gravity pull? Downwards. So it's always negative 9.8. Doesn't matter. If my ball is going upwards, which way is gravity pulling it? Downwards. At the very top, which way is gravity pulling it? Down. It doesn't matter where the ball is. Gravity still pulls it down. Doesn't matter where it's going, how fast it's going, any of those things. That's a really, really important thing. All right, so this term goes away. T squared. Oh, look, our negatives cancel. What a blessing, because time, you can't do the square root. You technically can do the square root of a negative. It is technically possible. It gives you an imaginary number. In physics, an imaginary number does actually have a physical meaning to it, but you don't start to use that until quantum mechanics, which you won't have to deal with in your life, very likely. So you're spared there. It has other uses when it comes to oscillations and things like that. But for our class, if you're taking the square root of a negative number, you did something wrong. That's an indication that something's wrong. All right, so yeah, you get t equals the square root of 3 over 4.9. And, you know, that spits out the answer of 0.78 seconds. Great. And remember, y'all, does it make sense? Does the answer make sense? You all have been around things that fall. Like you've lived your entire life. You yourself have fallen. So this is a really easy one. Unfortunately, I measured this roof. It's not quite 3 meters. This thing's, I think, fairly stable. Great. Yeah, so this is what's going on here. I am dropping something. Again, it's not quite 3 meters, so it's a little bit off. But, you know, if I drop this, 1, it's a little bit less than 1 second. It's around 1 second. This is around 1 second. Yay. It matches your expectations of reality. Something you might not realize is that things fall for a much shorter time than you might actually predict. Like this might seem really short. Gravity makes you go really fast, really quickly. Case in point, reminder to you all that 27 meters per second is roughly equal to 60 miles per hour. You know, let's just make this problem real quick. I think this is an interesting one to help you all remember things. If an How long does an object need to fall to reach a velocity of 27 meters per second? How long does it need to fall to reach a velocity of 27 meters per second, i.e. 60 miles per hour, assuming no air resistance? I think this is a really useful exercise to give you all a sense of scale. So yeah, try this one out. Write down your givens, missing, all that kind of jazz. The object starts at rest. An object starts at rest. How long does the object need to fall to reach that velocity? And this one I'll leave as a one for you to actually respond to.
No, it's awesome. It'll be fun.
Yeah, so what's my initial velocity? What's my final velocity? Which direction? Which way is it falling? Down is. Yeah, but that's good that you realize that, like, oh, the negative's weird, and you can see it fixed it. So anytime you get an answer that's like the wrong sign, it's generally some tiny thing like that. And you just look through your things and say, did I put my signs in the right place?
You can also just redefine your axis, so the positive direction is down.
What do you solve for x? That totally works. That totally works. You can straight up solve.
Yeah. But some of them are way after. Like some of the equations.
But what are you gonna do?
That's when you do the. You would add them together.
That would mean if you fall this far.
Yeah, but it's negative.
You can, yeah. So check out the equation. Here's actually what else you can solve. But you can also make it how far. But it will be much bigger than that. So there's the. Yep, think about it. So after 1 second, how fast am I traveling? My acceleration is negative 9.8 meters per second squared. That's how fast you run after 1 second. After 2 seconds, how fast you run? Rough. Yeah. Just 9.8. After 3 seconds. Yeah, but it's like 9.8 is roughly 10. It's like roughly 30, which is so after 3 seconds. Yeah. Which way is it? At the end, which way is it fall? All right, y'all. So let's work through this. What's cool is if you know it, if you understand the concepts, this is actually a very quick problem. If you understand, and I'll show you all what I mean. We'll do it the long way, and then I'll say, hey, here's the quick way to think about this to check your answer. Y'all tell me what's given. There's actually a nice thing in this givens I want to also teach. What's going to be negative 9.8? Beautiful. Acceleration, which is our gravity, which is our acceleration. What else? My initial velocity is 0. And then there's one more thing I know. Final velocity, what is it? 27. Which way is this thing falling? Up or down? It's positive or negative? Negative. If you got a negative time, this is why. So it's one of those things that you have to take into account, putting those positives and negatives and stuff like that. All right, we're solving for time. Great. The equation we're going to use is the V final equals V initial plus AT. We do the math. My final velocity is negative 27 equals 0 plus negative 9.8 times t. So that goes away. 27 t equals 27 divided by 9.8. The negatives cancel, so life is good. And I think you all got like 2.7 something. What was it something? 6? All right. So that's the answer. Something like that. I'm going to double check it to make certain I didn't hear someone wrong. 2.75 rounds it. That's fine. 2.755, 2.76. Great. So this is how you do it the rigorous way, the full on through the process. How fast is this thing traveling after 1 second? If I drop any object and there's no air resistance, how fast is it going after 1 second? 9.8 meters per second. What does acceleration mean? It means how much does my velocity change every second. So if I'm going 0, 1 second later, I'm going negative 9.8 meters per second. After 2 seconds, negative 9.8, and then another negative 9.8. After 3 seconds, negative 9.8, negative 9.8, negative 9.8. Acceleration is how much your velocity changes. So this problem, 9.8 is close to 9. 27 divided by 9 is about 3. After 3 seconds of free fall, if there is no air resistance, you're going 60 miles per hour. It's crazy how much gravity speeds you up. I mean, this is why asteroids come. Well, okay. Asteroids are already going super quick. But this is why anything that enters the Earth's atmosphere gets real fast, real quick. They did the whole person falling from... Gosh, the person that did like the highest skydive or something like that. Yeah, the man was going like, I think he was going faster than the speed of sound because he was up way above where there was air resistance. So the man went super fast. I think he blacked out or something. I don't remember why. He was spinning. Oh, no, okay. So he's spinning too and it blacked him out because when there's no air, a little bit of stuff can get you out of control. Whatever. He got going real fast. Then he hit air resistance and it slows you down a bunch. And there you go. But yeah, gravity is real powerful, y'all. You've been living in it your whole life, and you're just kind of used to it. I mean, you know this. You know if you jump off a second-story building or 3 stories, you're probably going to break a leg or something like that, unless you know what you're doing. But yeah, jumping off a second-floor building or a third-floor building, you're not going to be going 60 miles per hour. maybe like 30. You can do the math now. You have the physics. You can figure out how fast you'll go if you jump off of a certain height building. You have the skills to determine that now. How fun. All right. Great. Let's practice. Let's do this one now. This is another classic. If I toss an object upwards with a velocity of 3 meters per second, what is its velocity at its highest point? I'll even model it for you. There it is. 3 meters per second is not a super quick velocity. I mean, do the math. 27 divided. It's 1/9 of 60. It's about 6 miles per hour, give or take. At its highest point, what's its velocity? If you're doing math, you're doing it wrong. So I'm going to give you all 30 seconds. No math. And I'll keep modeling it for you. Just keep tossing this thing up and down. At its highest point, how fast is it going? At its highest point, if I toss it straight up.
Oh, yeah.
10 more seconds. In 5, 4, 3, 2, 1. All right. On the way up. So let's just draw a picture. On the way up, which way is it moving? Upwards. Is its velocity positive or negative? Positive. Great. On the way downwards, which way is it moving? Down. Which velocity, positive or negative? To go from positive to negative, you have to pass through a number. You cannot skip this number. That number is 0. You cannot go from a positive velocity to a negative velocity without stopping. Like you cannot, draw a graph of this. If I have a graph of velocity versus time, to go from this spot to this spot, I have to pass 0. You can't just skip it. And so at the highest point, it stops. You all have experienced this. If you've ridden any ride or something like that, you'll kind of go and you'll feel that like weightless, you're like, woo, you're just kind of hanging in air for a second. There you go. So this is an important thing. When we're solving physics problems, if I say, hey, solve how high something goes, I'm not going to tell you the velocity at the highest point is 0, but that's a given. This is a given you can write in a problem. At the highest point, the velocity is 0. And this is something you can add to it. Now, again, we're assuming straight up and down. And even if I wasn't saying straight up and down, the y component is all we're caring about here. Technically, if this thing's moving left and right, it can still be moving. All right, next question. Also a classic. Oh, and I keep forgetting to put the right answer for things, which means I have to go back and do it. It's very fun for me. Boom. Question asked. If I toss an object upwards with a velocity of 3 meters per second, what is its acceleration at its highest point? If you're doing math, you're doing it wrong. Again, 30 seconds. Check with your neighbors. If you have different answers, one of you is wrong or all of y'all is wrong. All right. I gave you all even extra time. What a blessing. All right. 5 seconds. 5 seconds. 4, 3, 2, 1. This answer is what it is, whether you like it or not. The answer is negative 9.8. That's just a fact. If you're in the air and there's nothing else, if you're in, nothing is holding you, there's no rockets attached to it, no motors, it's negative 9.8. Peter looks like he has something to say.
Not related to this. I was just a lot of people have been tripped up by the function notation thing, so I was gonna.
Oh, good, perfect. All right, awesome. I didn't know if you had something to add to this. So there you go. Negative 9.8 at the highest point, on the way up, on the way down, as long as there is not a rocket attached to it, as long as there is not something else propelling it or slowing it down, if gravity is the only thing affecting it, it's negative 9.8. And I'm just going to straight up tell you in 2D kinematics, if something's in the air, I'm not going to have any motors attached to it or air. A will be negative 9.8 when we do these problems. And to clarify, not just any A, but the A in the Y direction. That's something I want to prepare you all for 2D motion. Just in the up-down. Gravity does not make things move left and right. Gravity does not affect the X component. Case in point, every single object in this desk, we're not worried about it flying off my desk. Because gravity doesn't make things move left or right. So, foreshadowing. All right, there you go. That's a little cheat sheet. At all times, G equals negative 9. G equals A equals negative 9.8. I'm even going to put the little subscript here. Always got to remember what the buttons are. Wrong one. And that's the wrong. What's wrong with this, ants? What's wrong with this? Y'all tell me. I just spotted it. Yeah, good. The units are wrong. All right. Object slows down on the way up. Object stops at the top. Object speeds up on the way down. On the way up, velocity is positive. Object stops at top. Velocity is 0. And then on the way down, velocity is negative. On the way up, the velocity and acceleration are opposite signs, so they fight each other. On the way down, velocity and acceleration are the same sign, so they're helping each other. So this is, for me, where physics starts to get fun, when we actually get to use it. So I'll be honest with you, I was telling my wife, like last Thursday, I was like, man, teaching's been boring. I was like, what's up with this? It's because the beginning 2 weeks is me teaching you all a bunch of definitions and like rules and things like that. It's super boring. Now we're at the point where we're actually getting to enter into problems and solve things, and I can connect it to other things you experience in life. Way more interesting and fun to me. You all experience all this stuff every single day. The benefit of physics is now you can understand a little bit more details why. You can predict things a little bit better. You can understand things better. Again, you all been living in this world, and you've been living perfectly fine. Not knowing physics isn't going to hurt you. But knowing it does make the world a little bit more interesting. Lets you see a little bit behind the curtain, understand details, and stuff like that. All right. This is another important question to this is a tool that we're going to do. I toss the ball upwards. How does the time to the top compare to the time from the top to the bottom? So, to reword this, because the wording here might sound a little weird. I toss the ball upwards. It takes some time to reach the highest point. It then falls back to my hand again. How does the time from the bottom to the top compare to the time from the top to the bottom? How do those two times compare? Bottom to top, top to bottom. Is the Are they the same? Does the time 1, is it greater than time 2? Is time 1, that's the beginning, less than time 2? Assume no air resistance, always. Assume no air resistance.
Where did that come from?
All right, 10 more seconds. Put your guess, no math here. Unfortunately, I can't really prove this one super easy without the next one. Well, I think there's a way to prove this without, but all right. In 5, 4, 3, 2, 1. Boop. All right. How does the time compare from the top to the bottom? They are the same. So if you just watch something go up and you go down, it's a very symmetrical process. And actually, if you took a video of this and you played it in reverse, you wouldn't be able to tell the difference between the two. Video, and you can kind of check this for yourself. If you record a video of something going up and then down, you play it in reverse, it's going to look at, my hand's going to look a little weird. But it's the same thing. So mathematically, you can kind of prove this. You can do the math. If we made up numbers and said how fast was it going initially and all that kind of stuff, you can do it. This next one also is going to help us. It's going to make it a little bit easier to prove. Well, it's kind of related to it. I toss a ball upwards with a velocity of 10 meters per second. What is the velocity when it returns back to my hand? Whatever. You got 30 seconds.
Is part of the reason why you're using a baseball because it doesn't have as much resistance?
It's also laying in my
Oh, okay.
Yeah, it's convenient. Yeah, baseball's really convenient. But yes, a baseball doesn't have too much air resistance until you get going really fast. Baseball's really nice. And that's most objects. Air resistance doesn't affect very much. Like most things going through the air resistance does have some minor effect. It is amazing how close you can get to the answer if you just ignore air resistance. Maybe air resistance gets you that last 10% for most things. If something's going really fast, then air resistance makes it huge. Really fast or really big surface area, then it makes a huge difference. But, yeah. All right, 5, 4, 3, 2, 1. Baboop. All right. So again, there's symmetry here. If it leaves your hand with 10, it returns to your hand with 10, but it's downwards. Positive and negative. If you say it returns to your hand with positive, that means it's going upwards, which just doesn't match reality. When it returns to your hand, it's moving down, not up. So negative matters. It sounds, again, I'm going to keep saying, it sounds like a stupid tiny detail, forgetting the positive or the negative. But it makes a way different answer. 10 plus 10 is 20. 10 plus negative 10 is 0. The answer between 0 and 20 is drastically different. If you don't have the right sign, it can make your answer drastically different. And with engineer, and this is just true of anything you all do. If you put in your balance sheet, if you all are doing your budgeting and you put plus 1,000, that is way different than putting minus 1,000. That's the difference between gaining $1,000 or losing $1,000. There's lots of cases in your life where a positive and negative will mean a drastically different thing. Tiny little detail with drastic consequences. Okay. So this is a problem from 1D kinematics. It's at the very end. I don't even know if it's number 13 anymore, but it's in there. Calculate the displacement and velocity at the following times: 0.5 seconds, 1 second, 1.5 seconds, 2 seconds. For a ball thrown straight up with an initial velocity of 15 meters per second, take the point of release to be y naught. You all have everything you all like skill-wise. Do it to it, y'all. You are prepared for this. Work together. We're here to help you as well. Go through the process. Yeah, those last two are always a pain. You can take one of them and give it for the other. But not either one did. Oh, the joke. We told it on Thursday. Choose.
No, I would say with software.
And whenever you're ready, just.
Mm-hmm. And you're given the initial too. So,
in these seconds that you're doing, like second, is it released and is it going up? Because then that would be positive, right? No, we're slowly just, oh yeah.
oh wait. Oh wait. I repeated the like not the one on the bottom.
So,
Okay. Yeah, that one.
oh, I guess maybe the first one. So
Oh, that's fine. Like you don't want to. Should I do it here?
and there.
I was like, if you're right, it's like there's no pressure. You're doing us. I don't really care. Like, never be fair. You got to do it. No, I know.
Yeah. But the seems to work too than the average.
The good thing is, both like,
It's not that much.
because you got two things you're solving. In one case, you're solving for velocity. Oh, this is so that one works. You just do the same thing. Y final minus y.
Yeah.
The displacement.
There you go. Both equations are necessary.
Oh, so you take
You just do them ahead plus that.
So you take your
Yeah, 15 plus this, so I plus 500 which gets me 4.9. Oh, yeah, 10.1. So negative 9. Yes. 10.1. That's for G, right? Yeah.
Change the position, which will end up being a y final minus y actual or initial 0.
1/2
Oh, that's
Yeah, you can do either or. You can find, so it turns out both you can find each other. Use an equation to find final velocity, an equation to find final position.
I was in the third one.
Yeah, you can't do both. You can't solve for two different things at the
So,
same
but
time.
then.
It's not gonna happen like that. Sure, it's lots of things.
That's true.
Yeah, so always trust the equations. Yeah, there's generally not too many shortcuts.
What's our
That one looks pretty
our
uniform.
our X initial is 0, right?
Okay, let's check. What do you solve?
We're solving for displacement. We're solving for X now. And so our X is 0, our X initial
We wanted
is
to have
0.
like each of them both the same. Alright.
Oh. I'm usually the third, the second.
Your initial velocity. Your initial velocity.
No, I know.
Remember, part of this problem is finding we don't have it. Yeah, they said today in this problem. Great, this is on the final position. So you got two unknowns.
There's no wrong.
I know.
Perfect, that's exactly.
It was 6.2, right?
Yeah.
I don't know if it really does.
Sure.
I do the same thing for the other time.
Sure.
And that.
What was your time? 5 seconds. It's actually probably gonna be past there. Yeah, we'll be into the ground somewhere. Yeah, I don't even think it travels for 5 seconds.
So for C.
So, it's not. It also not. It goes up and it goes down. And if you were the answers that gives the check your work, show that like it goes up and then by 2 seconds it starts.
Oh.
But you can't assume that at some time it's already.
Oh my god, that makes so much sense. But yeah, that is true. It's the same.
Yeah.
It's empty. There's still about 80 people responding.
Yeah.
Are still.
For some
Yeah.
reason I thought
Which I'm fine with. I don't really care what people are.
Yeah, I noticed, like, over there, you sit in all one.
Yeah. There's a whole table abandoned. All right. So I'll just write down the givens as a checkpoint. I think I'm looking around and people are doing a fantastic job. If you've been solving for y final, it does work out because my initial position is 0. If your initial position is not 0, then it doesn't work. So if your initial position was anything other than 0, 5, 10, 15, whatever, you do have to kind of actually solve for the whole thing. So I just want to mention that. You might be solving for y final and not realizing you are. It does work out in this problem. It will not always work out this way. The joke? It's up to you. We can finish it. And then, as long as we remember, I just forget these things. I was like, as long as you don't forget, because I will forget. So the two choices here, I think a lot of people have realized this. This first equation will give you final velocity. And then this second equation will give you final position. But again, there's so many ways to solve this. If you find initial velocity or final, like you can do so many of these. You can also do VF squared equals V naught squared plus 2A delta. Like, the third one, if you like wanted to, if you found the final velocity, you could plug that into that one and then do it. It works. The only thing I want to note to you on everybody, I've seen this with a few people. I want to remind you, anytime you do a square root, if I do the square root of 64, there is 2 possible solutions to this. Plus or minus 8. And you have to make a judgment call on which one's correct. You have to make a judgment call on which one's the right one. In this case, is it going up or is it going down? Or if you're doing time, it's always going to be positive time. We're never going to do negative time. So I just mentioned that because that's a common thing I've seen. I want to make sure everyone kind of recognizes that. Okay, but the first 2 equations here will get it done for you. The third one, if you did it that way, it's totally valid. And I also want to just acknowledge it's an option. And we'll resume stuff in like 10 minutes. So you can finish this up and then do whatever. Or you can stop. I don't care. 9:27 is when I'll start yabbering on about 2D kinematics. So whatever you want to do with these 10 minutes, up to you. Oh, there's a joke though. Sophia's got a joke. Here's your mic.
Alright, so.
And if you wanted to check your work, you could do it.
Okay. At the zoo, there was a baguette in a cage. It was bred in captivity.
You got 10 minutes to do whatever you want. Once you solve. When? I think February. Braille. Let's see. I can do a FaceTime call. I know who's talking. So this week we're doing 2D kinematics. Next week we're doing forces. The week after that we're doing forces. Yeah, we got, including this week, 3 more weeks of content. 2D kinematics and 2 weeks for forces.
Just so I know what.
Okay. Now, and you'll start to see more and more people. But also, if you go right this way, you see encourage them to help you. Anything you can do to reduce that barrier. Now, I will say this copy is 3 minutes on these resources. So thankfully, they can take advantage of this. I've only had a few people in line. And last semester I had, now granted I had way more students, so that also increased the chances, but it was not uncommon for me to have like 5 people at a time in line, but I'm not there yet. And granted I have less students this semester than I did last year, but I also expected a higher proportion of students. We'll see as time goes on, it'll vary, and then also you'll probably get from other classes and things like that. It's really going to start happening every semester. Not necessarily, yes, with these classes, but also all the other classes. Test work. Maybe more than that did not do what they needed to. They didn't realize anyone was waiting this, or just they didn't know what they were doing. It's nice actually getting into stuff. All right, so what are you taking any classes or anything?
I am not. I'm finished with classes.
Well, I'm still going, so I want you to so I move away from my computer during this time. Maybe we'll ask me questions. Yeah, so yeah, okay, so you're doing this. So for the masters, class-based, so like this for thesis.
I didn't even do thesis. I was originally going to go for
It's so sure. Yeah, that's fair.
Because my research is like machine learning.
Interesting. Yeah, does that extend to all programming?
But I think I haven't ruled out coming back to either here or somewhere else and actually doing the rest of the PhD. But I'd want to, I think, be doing telescope observation.
Have you chatted with
Yeah, I think my next step is going to be to do something else. So I'm interested in education, communication type stuff. So I don't know about teaching science.
You get a lot of motivated students, you get a lot of fun. You do stuff like that. If you have lower level, just be prepared. Most of the job is motivation. Try building relationships, which is still good, but it might be different than yours. Question?
The question, yeah.
Yeah, sure. That's it.
It was question 4, but part B.
All right. I'm gonna warn you, stream's going, so
Okay.
anyone, I don't really care, but okay.
I'm just confused by the wording. It just makes no sense.
This one?
to me. Yeah.
So the difference here is this one they did the distance.
Yeah.
So we found speed by just doing distance divided by time.
Right.
This one's velocity, which we only care about. So instead of using this, we use the final minus in it. Like we only care about the where you stopped and where like the positions.
It's just it says magnitude of the average velocity, and like I know it's 10.3 over like
Yeah, because remember, average velocity is just
yeah.
delta x over delta t.
But I don't know how you get that from like the way it's worded, magnitude of the average velocity. Like I'm thinking like I don't know. In my
It's the same
brain-
thing. Magnitude just means what's the number. Like, so magnitude is the amount. What's the number
Oh,
for
it's
it?
just like asking for the positive.
It's just asking for the number. Yep.
Okay.
So it's basically saying, hey, there's some arrow. How big is that arrow? And
Is it just giving all that extra
What's the
information
direction?
to trick with you?
not necessarily a trip with you, just kind of can you decipher it? Can you interpret? So magnitude, remember, just means how big is my arrow. I don't
Okay.
care about positives or negatives. How big is the arrow? Generally associated with that is also what direction, because you have the how big is the arrow and in what direction is the arrow.
Gotcha.
So yeah, you're gonna see the word magnitude to go to mount. The magnitude is the word we use to say how big is it.
Yeah.
So you have how big the arrow is and in what direction it is, and they're two separate things. And if I have those two pieces of information, that gives me everything.
Okay, so it was a lot simpler than
Yeah, it's that easy.
Okay.
It was just taking, hey, average velocity is this divided by this.
Okay.
I don't care about the direction at this point. If I cared about the direction, it would just be that angle.
Yeah, I thought this like information was relating it to this other information
Nope,
here somehow.
just additional information that don't care about.
Gotcha.
Because all you care about is I started here, I ended here.
Got it.
Yeah.
Okay, perfect. Thank you.
Yeah, no problem. Hey, what's up?
Okay, wait. First off, I was doing your work, but like if I know how to do a problem, like if it's like when I look at it and I can figure out the process without writing it, I generally don't write it. But I was doing.
Oh, no, you're fine. You're fine. Sorry.
And
Yeah,
then,
I have no.
And also, could we have done the one that's like the final position is equal to initial position?
If it works, it works. Did it work?
Yes.
It works. As long as you have everything you need and have, as long as you have, as long as there's only one unknown and you know everything else, you can use the equation. Yeah, no problem. Yeah, no, I generally just look around and if I see a blank paper, I assume that means people are stuck. Is my assumption, because generally, if that's not the case, just let me know. So that's when I'm walking around and I'm looking at people's papers, is to try to find people that need help, and I base it on what they have written down. If they have stuff written down, I assume that doesn't mean I'm always right on that. Yeah.
As a Aquarius, you feel like you at least look at it.
So, I think like when I add physics, it's also
Oh, yeah.
Is this like required?
I need to remind people of that. Thank you for letting me know. No, but it's worth. So I sent an announcement about it. If you complete it, it adds 0.5% to your final grade as extra credit. Just if you do it. Like, it's not based on how well you do. The reason for this assessment is it gives us a way to compare classes. It gives us a standardized measure to determine how we're doing. Yeah, I'll mention it in a second. No details. All right. All right. Someone just raised a really good point that I want to mention. I forgot to mention it last class. There is a separate web courses that you all been enrolled in. I can't even open it because I don't have access to it. That's called 2053 Assessment or something like that. I sent out an announcement about it. Probably the most important thing for you all is if you do that assessment, 0 effect on your grade. It is only extra credit. Let me just state it that way. It's only extra credit. If you do it, you get 0.5% to your final grade in this class. If you do, there's a pre-assessment, and at the end of the semester will be a post-assessment. If you do the post-assessment, you get an additional 0.5%. 0.5 plus 0.5 is 1% to your final grade. doesn't sound like a lot of points, but another way to phrase it that makes it sound way better is 1% on your final grade ends up being the same as adding 6.67% to one of your test grades. It's equivalent to that if you do the just conversion. So that makes it a little bit more motivating. The reason for this, so this is a standardized test that all the 2053 students are given. And the benefit of it is it lets us see how we're doing as a department. If you don't have a standard, you cannot unfortunately use grades as a standard for understanding. Like every instructor is slightly different in how they do things. But if we give every class, it's like taking the MCAT. The MCAT, everyone's taking the same MCAT. You can compare things. This is the same idea. The reason we do a pre and a post is you all come in here with different levels of understanding. So if you come in here with a lot of understanding, you're going to come out of the class with a lot of understanding because you came into it with that. So we have to have that standard to kind of compare to see how much, it's called learning gains. How much did it actually go up? What did you start with? What did you end with? How much did it go up? If we just take the post, you neglect that some people might have come in with a bunch, and so you can't make the assumption, oh, they scored high, so the teacher taught really well. Maybe, or the student already knew everything coming into the class. So that's the reason for it. It's just interesting education stuff. Anyway, so I appreciate if y'all do that. It's very useful for me. I just get a list of, so I will get a list of all the people that did it, the pre and the post. I'm not going to add all these points to like the very end of the semester. Maybe I'll make an assignment for the pre or something just so you can see. But so this really only affects the final grade at the end. But then I will get some list of like the scores, but it's not tied to your name or anything. If that's a concern. I mean, I see all your all's test grade anyway. But this one I just get at the end, hey, here's all the different scores and things like that. And it's nice for me. Lets me know how I'm doing as an instructor. Just like I try to give you all feedback, it's good for me to get feedback. We're all trying to improve, right? Okay. 2D motion. It's the same as 1D, 2D kinematics is the name of this slide, but I just replaced the word motion because they mean the same thing. If you had so much fun doing 1D kinematics, it's doing it twice in the X and the Y. Here is the most, like how big can I make this? Where is it? Is it here? All right. The learning objectives. This one is like, I'm just going to make it ginormous and then like bold it. If you're good with 1D kinematics, all you have to do for 2D kinematics is realize that X and Y are independent of each other. We're going to get all the variables for X. X initial position, X final position, initial X velocity. And every time I say the word X horizontal, where am I located left, right? How fast am I moving left, right? What's my acceleration left, right? Great. That's a list of information. Then we're going to do it for the Y. Where am I located up, down? How fast am I moving up, down? What's my acceleration up, down? And we're going to do two different kinematics. Like we'll do kinematics in the horizontal, kinematics in the vertical. The only variable that goes across both, the only variable that is true of both is time. Time is independent of left, right, up, down. Time is the universal kind of variable that applies to all, horizontal, vertical. This is the name of the game. This is literally the only thing I'm really teaching you in this entire PowerPoint, and it's just practicing in various contexts. Split things up into X and Y. There's no new equations. There is no new concepts as far as any other than split up X and Y. And then it's just using all the stuff from 1D kinematics. So that's the name of the game. You're going to hear me say it again and again and again and again and again. Because even though it's such a simple idea, it just sometimes takes a little bit to click into place. But once it settles into place, if you can do 1D kinematics, you can do this. All right. But that is the name of the game. You're going to hear me say it again and again and again. Because if I can make you understand that, easy. No problem. All right. So you do have to remember vector notation. You got to remember the definition. Like it's just all the stuff we've already covered. Again, pretty much this entire thing is just applying this twice. So all the kinematics equations that we just used in the y direction, acceleration is negative 9.8 only in the y direction. Only in the y direction. That's going to be a theme. But yeah, this is nothing. This is just the stuff I've already taught you up to this point. The kinematics equations, the definitions of the variables. And now we're getting to apply it to 2 dimensions. All right. 2 dimensions. Not only can you move left to right, you can also move up, down. It's just saying what's the difference between 1 dimension, 2 dimension, 3 dimension. 1 dimension means you can only move in a straight line. 2 dimension means you can move in 2, like a flat piece of paper. 3 dimensions, we're never going to bother with it, but it's the world you exist in. I can move left to right. I can move up, down. I can move in, out. The world is 3-dimensional. If we really want to do things in the world, we got to do 3-dimensional, but you're spared. If you can do 2-dimensional, 3-dimensional is just doing kinematics 3 times. So there's not much additional benefit to it. And it's really hard to draw 3-dimensional stuff. So don't worry about it. Okay. Oh, look, it's the same thing. I said before, X and Y are independent of each other. Whatever happens in X is independent of Y, and I will do my best to convince you of this. Where's my baseball? All right. This is something that for some of you will click very easily. For a lot of y'all, it's going to be a weird idea. However fast something is going left, right, has no dependence on its up, down. So one of the things you can do for yourself to test this is if you're walking, all right, great, I'm walking. Let's say I'm moving 2 meters per second. How fast is my baseball going? 2 meters per second. Fun fact. Which way am I going? Left, right, or up, down? Left, right. Great. So if I'm going to the left, 2 meters per second, so is the baseball. What's interesting is if I toss it upwards, directly upwards, it stays in line with me. Just because it left my hand, if I toss it directly upwards, if I give it a velocity upwards, it does not affect the left and right. You can test this for yourself. Walk around, do your best to toss something directly upwards, and you will find that without moving your hand, it returns right to it. As long as you toss it directly upwards, I don't have to think about it. I don't have to move my hand. It keeps moving at 2 meters per second. And because I'm also moving at 2 meters per second, it returns back to your hand. There's a demo that shows this that fortunately I didn't get, where like you have a cart and it shoots a ball up and then it returns right to it. The other easy way to prove this is if I'm walking and I let this thing go, its velocity doesn't turn to 0. That's something that like people think of. It's like, hey, if I let something go outside the car, it immediately, its velocity is 0. If you let something go outside your window in a car, if you're going 60 miles per hour, that object is going 60 miles per hour. Just because you let it go doesn't mean it magically immediately stops in place. That'd be like if you all were driving and you drop something, it like hit a brick wall. Like if you're walking and I let this thing go, it keeps moving with me. It keeps moving with me. It doesn't just stop in place and plummet to the ground immediately. So this is another, like, it doesn't matter what happens in the, yeah, sure, this thing started falling. The Y changed, but the X stayed the same. X and Y are independent of each other. If you drop a bowling ball out of a car and the car is going 60 miles per hour, that bowling ball will also be going 60 miles per hour until it hits something. So there you go. That's something. If you actually want to make your velocity zero, I need to find this video. If you actually want to stop when you get out of a vehicle, you actually have to like jump backwards out of it. You actually have to push yourself the other direction. You can't just hop out of it. And you know this, if you hop out of a vehicle, you don't just land on the ground real nice and like, yay, I stopped moving. If you hop out of a vehicle, you are still going and you will roll on the ground a bunch of times because who cares what happened left, right? You're still moving forwards and backwards. Great. We're going to practice this a bunch. Look, these slides aren't anything fancy. They're just saying, hey, everything you all did for one-dimensional, now we got 2D. You do have to remember your vector stuff. So basically, here's how these problems are going to go. You're going to start the problem. Split everything into X and Y. Do all the math in the X. Do all the math in the Y. And then at the end, recombine them back together. It's vectors, y'all. Remember that was how we did vectors? You got them into components, X and Y, and then you had to bring them back together at the end after you did all the math. It's a lot of fun. So much fun. It's a little tedious, but there's no shortcuts, y'all. It's not like I'm teaching y'all one way and then a week later I'm going to say, but here's the shortcut. No, there is no shortcut. This is what you got to do. Like, this is it. If there's a shortcut, I don't know about it. Okay, so yeah, let's make certain you are solid with this. It's been a week. Not been a super amount of time. Here's a triangle. Here's my displacement, and I need to break it into X and Y because I'm about to do some 2D kinematics. if I want to find the x component, i.e. the horizontal component, the triangle's already drawn for you. How kind of me. How would I do so? And it's all in variables. So how's your trig? There's only one right answer. Don't like the variables, make up numbers for them. You're like, man, I'm really comfortable with numbers. Make up numbers. You're allowed. You can make up numbers for the things you don't, that you know. We know R, we know the angle. SOHCAHTOA.
No, that's the one that I do now.
Well, that's what you're gonna. So that's how you're gonna do this. So you know the angle. What side are you solving for? Which one's the which side is next to the angle? Is that one next to the angle?
Oh wait, that's not the angle. Oh no.
Yeah. 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 No, they're good for you. Look, they only got 3. Could be worse. Could be a hexagon. I know they are, but they have 6 sides. We're only working with 3 sides here. I do love the angles. No, their angles are really awful. It's going to sound really silly. So just remember the definition of the word opposite adjacent. So there's my angle. Adjacent means next to it. Which side is next to it? That's the adjacent. Opposite is the one that's, yeah, it sounds really silly, but that is, and that's what the definition comes from. Yeah, so that's literally what I do. I just look at it and say, oh, adjacent is the one next to it. Hypotenuse is always the height, and that's the hypotenuse is always. So that's never even, yeah. All right, 20-ish more seconds. SOHCAHTOA, y'all.
Oh, no, that's not the hypotenuse.
I should not be an engineer.
All right, 5, 4, 3, 2, 1. So SOHCAHTOA, that is one of those. Mitochondria is the powerhouse of the cell. SOHCAHTOA is in that same category. It's just too useful. Now, this is the hypotenuse. The question I get, and this is a valid question, and it's one that you have to decide. It's really the challenge here. Which one's the opposite? Which one's the adjacent? It sounds maybe a little silly, but it is just like this is the skill. That is pretty much the most common reason you mess this up is either you just jump to what you think the answer is, or you don't think about which one's the opposite. Adjacent is the one next to it. The one next to this angle is this one. The hypotenuse is always the hypotenuse. Like that one just gets ruled out. That one's never the opposite or adjacent. It's just, it gets its own name. Adjacent is the one next to it. Opposite is the one across from it. So that's how you decide. Great. Which one are we trying to find? We're trying to find the opposite side. So we're not going to use cosine because it doesn't have opposite in it. Tangent would work if we had the adjacent side, but if you notice, none of the answers have a delta y in them, so that rules out that one. So we then write out this. Sine of theta is opposite over hypotenuse. We then write sine of theta. We actually put what they are, delta x over delta r. And then how do you get delta x by itself? You multiply delta r over. Variables are just a placeholder for a number. That's all a variable is. So you can move them around as if they're numbers. They follow the same logic. And in fact, if you became a physics major, you would stop using numbers altogether. Like, it's all variables. Because if you can set up this equation, now I can do this for any problem. Any angle, any side. I have a solution that works for any of it. I have a general solution. The reason for this is people get in the really bad habit of saying delta x is the cosine. It's a habit that forms because it's very often the case, but it's not always the case. So I specifically give this problem to show you all the x component is not always cosine. Do not assume it is cosine. Think through this. You have to think through this process. Yes, it takes a few extra brain cells and a few extra seconds, but if you don't, you run the risk of getting the answer wrong. So it's not a thought process you can skip. You cannot just shortcut and say the x is always cosine, because it's not always cosine. It depends what angle. If I had instead given you this angle over here, then yes, it would be cosine, but I didn't. And sometimes you have different angles. All right, ready to answer this one today. This was just a review question if I'd happened to teach this in the next class and we'd forgotten some things, but we already did those, yay. Okay, this is just a reminder. Triangles, if you want the magnitude of something, you take the x squared plus the y squared. If you want the angle, tangent inverse of y over x. Just reminders of things that we've already covered. Okay, make certain we're cool with this. A bird flies 3 meters east and 4 meters north. What is the bird's net displacement? These are very nice numbers on purpose. The best triangle. We're big fans of this triangle. Yeah, just one of those. It's so nice.
I'm not sure if it'd be the math together or just some.
X and Y.
Oh my gosh. Yeah.
Yeah, I think so. Okay, cool. So yeah, that is how we do that, isn't that? Where it's like,
Yeah.
oh yeah.
Yeah, they hated it.
And to get a more accurate score for the circle, they draw small.
Sure.
Wait until you learn about sequences and series and you have to find out whether they converge or diverge and by how often. He's so hot. I hear it's so bad.
All right, 10 more seconds, y'all. And 5, 4, 3, 2, 1. All right, it is one of the benefits of being in class. If it's like, just forget to. That's why I do the countdown for all that reason. And so if you still have an answer, just like holler at me. All right, 1-0, great. All right, first step is practicing drawing our pictures, making sure we can draw the triangles right. I saw people do this, but and for the most part, they're pretty good. But one thing I want to note, remember, it doesn't matter which one you do first because it's addition 3 meters east. So I draw an arrow to the east. That's 3 meters. And then your next arrow starts where that one ends. And that one goes 4 meters north. And you make a triangle like this. If you drew a triangle that was instead like this, you might get the right answer for the magnitude, but your direction is wrong. So when you get the direction later, you're going to find that this thing points up to the left. But again, think through the logic. East means I went to the right. North means I went up. My final arrow should point to the right and point up. Whereas if you draw this triangle down here, this one points left and it points up. So how do you draw the correct triangle? You draw one arrow at a time. Where that arrow ends, you then start drawing the next one. And that'll guarantee you do it right. In fact, you could do this. You could do 4 meters north and then 3 meters, and you get the same result. If you draw the arrows appropriately sized, you get the same arrow. Anyway, great. We're finding the side of a triangle. It's square root of 3 squared plus 4 squared. This is a beautiful triangle. It's the 3, 4, 5. Big fan of the 3, 4, 5 triangle. There might be a couple other triangles that do this, but that one's great. Okay, just a reminder to y'all, velocity. Look, instead of doing it in 1 dimension, we're doing it in 2. It's the same slide as one-dimensional motion. Just now there's a J also involved. It's just don't stress this too much. This looks worse than it is. Don't really worry about this. This is just definitions of what velocity is. Don't worry about this really too much because I think this makes it look worse than it actually is. This is just definitions. Hey, if in 1 dimension it was just the x, in 2 dimensions, now it's got an additional term to it. Yay! But if you want to combine them, square root of that squared plus that squared. So don't worry about that too much. Definitions. I'm not going to test you on don't stress it. How do we find, oh, look, it's a triangle again. If you have the x component and you have the y component, yay. You can do a triangle. I don't know why I put these deltas here. Let me actually get rid of them. The deltas here don't really make sense. So, ta-da, they're gone. And now it makes more sense. If I have some velocity and I want to get it in its x and y component, what do? I make a triangle. And I break it into its x and y. Just because they have different letters next to it, it's still a triangle. If you're cool with triangles, you use the same skills. It's the same exact skills that we used on this one up here. They just had different letters next to it, but the same skills. Okay. Let's try this out. A bird flies for 2 seconds and makes it 3 meters east and 4 meters north. If the bird is traveling at a constant velocity, what is the bird's average net velocity? It does not tell you how long it traveled east. It does not tell you how long it traveled north. It just tells you how long it took total. It tells you the total time.
Yeah. I don't think. Oh wait, he did it. Oh, 7 to 20.
No gravity here, y'all. My bird is not going up or down like it's going on a horizontal plane. Yeah, no gravity. The bird is not plummeting to the earth. That would make it a three-dimensional problem.
Oh, okay.
But like, we don't have. Oh no, it's because it's that so if that's for the magnitude. You told me that. And when you're outside, like, oh, it's like
The net velocity Okay, I was about to say, bro.
All right, give y'all 10 more seconds. And 5, 4, 3, 2, 1. So this one really just boils down to if we're asking for the average net velocity, V average is going to equal delta R over delta T. How far did I go? What's my displacement? What's my time? Which equals, we found this previously, was 5 divided by 2. So remember, y'all, 3 meters this way, 4 meters this way. Delta R is this side. So it's the 5 that we found previously. So this is saying, hey, average magnitude, we combine our x and y's together, and we then divide it by the time, and that's great. And that's for the average. That's for the average. The average is a pretty boring quantity to find, but it's actually generally like one of the more straightforward ones to find for this reason. A lot of our problems we're actually going to find instantaneous. We'll do a couple of different strategies for it. So this is just a simple case of, hey, if you know how far it went and you know the time, you can just divide those two. And it's nice, easy peasy. Okay. A bird flies straight 45 I don't know why it says straight. A bird flies, that's a typo. I mean, I guess straight is important. It doesn't make a squiggly line. 45 degrees east, a distance of 95 kilometers for 3 hours, with the x-axis due east and the y-axis due north. What is the displacement in terms of the unit vector? What is the average velocity? These answers unfortunately give away too much. Whatever, I'm just going to talk about them because they're kind of right here. Oh, look, we just took what's the displacement? You just take this. Let's draw it real quick. So really, if your picture is good, this is easy. 45 degrees above east. So if we draw north, south, east, west. Remember, never eat soggy waffles. You do not need to know this for the test. On the test, I'll just say up, down, left, right. So 45 degrees above east. East is the positive x-axis, so that's 45 degrees. And I'm just saying, hey, make a triangle. Find delta y. Find delta x. I give you the hypotenuse. So then find the x component, find the y component. And then for velocity, you're just going to, again, do the displacement divided by time. Nice and straightforward. So I'm not going to actually, this is one that, try it on your own. Don't look at my picture when you're doing it. Draw the picture yourself. That's really the exercise here. Can you draw the picture? The answer kind of gives it away too much, which is why I drew it for you all here. But next time when y'all try this on your own, don't use the picture. Draw your own. All right. Great. We're almost getting to the interesting problems.
If you already know what
Acceleration. Oh, look, it can be in multiple directions. It's just, hey, we did it once in one dimension. Now add another dimension. This is the one. So exciting. Very, very great. Again, this slide, really, there's nothing much new here for you to really note, so don't worry about this too much. It's just definitions. It's just making certain you know, hey, this is how we can write it. We can write it in x and y, and, if it's good for one dimension, change in velocity over change in time, great. Do it for the I and the j. It's really just showing you got to keep them separated. That's really the theme here. All right, woo, okay. Look, there's the equations, the kinematic equations, nothing new here. I put all the exclamation marks in bold and caps because it's so important. X and Y are independent, meaning when we start to use these equations, I should never see you put an X velocity in an equation that has Y position. I should never see you put a Y position in an equation with X acceleration. Keep them separated. You should never have horizontal variables and vertical variables in the same equation unless there's only one case of this if you're doing Pythagorean's theorem. That's the only time where you then take the x and y and combine them. That is the only equation where the x's and the y's go together, and that's literally because the purpose of it is to bring them together. How do you find the magnitude? Square root of x squared plus y squared. Time is also the only variable that does not have an x and y component to it. There is no horizontal or vertical component of time. Time is just a measure of the universe what time is fun. Yeah, try to define time to other people. It's a fun thing to do, fun exercise. What is time? You all have a sense of what it is, but man, when you try to put it in words, I'll let you do that yourself. But you know what it is enough to do these problems. Okay, great. All right. Now we're going to get into projectile motion. This is pretty much all projectile motion. A projectile is something moving through the air. That's it. It's something moving through the air. Projectile motion. It's a projectile in motion. To prepare us for these problems, I want to make certain we have a sense of this. I throw this baseball at the wall. What is its acceleration in the y direction when it's in the air? You throw something. I don't care what you throw. The second it leaves your hand, after it has left your hand, what is its acceleration in the y direction? This is critical. This question and the one following it are critical before we actually do any problems. If you do not know, so that's why we're doing this. Throw something. What's its acceleration in the y direction? The up, down. Thank you. I'm a fidget object. Yeah, it's spooky.
Slightly.
Yeah,
I should bring in my juggling beanbags.
Huh?
I should bring in my juggling.
Yeah.
As an excuse.
That's something I end up doing during my final exams in high school. Is I practice my juggling. I'm not very good at it.
The next one's
But it's a fun thing to do. All right, 30 seconds. Don't be so kind. No math. If you're doing math, you're doing it wrong.
Who's pushing you with your gravity hits it.
You're only meant to
All right, 10 seconds. And 5, 4, 3, 2, 1. All right. I toss this baseball up in the air. What's its acceleration when it's in the air? Negative 9.8. Its acceleration up, down is negative 9.8. What if I was in a bus going 60 miles per hour and I tossed this baseball up and down in the bus? What's its acceleration in the up-down direction? Negative 9.8. Even though the bus is going 60 miles per hour left-right, who cares? That's the X direction. Doesn't matter. Even if that bus was speeding up or slowing down, don't care. My baseball is only in the up-down direction. My acceleration in the Y is negative 9.8 meters per second squared. Gravity is the only thing making this thing go up, down, like making it get pulled down. It doesn't matter how hard I throw this. The only thing that matters here is as long as it doesn't have a rocket on it or a jet or wings or things like that. And no air resistance. Great. So that's the key point here. All right, we did the Y direction. Maybe you can guess what's going to happen in the next one. What about in the X direction? We are no air resistance. No air resistance. I throw the baseball. Hiya. What is the acceleration in the X direction after it has left my hand? It is not touching my hand. That is critical. I don't care if it's here, here, here. It's just not in my hand anymore. What's the acceleration in the horizontal direction after it has left my hand? No air resistance.
So we don't accomplish like
You can do it.
No air resistance. All right, great. You got really quiet. So I'm just going to 5, 4, 3, 2, 1. So, if you, this is all about, again, there's some memories, whatever. What is acceleration? If something's accelerating, what is it doing? Speeding up or slowing down. We'll eventually find changing direction as well. But speeding up or slowing down, is there any, after it left my hand, is anything making it go faster or slower left, right? No, there is nothing pushing it forward. There is nothing pulling it backwards. There is nothing pushing it horizontally. The only thing affecting it is in the up-down. Gravity is pulling it up-down, but gravity does not make things go faster left, right. Again, we're assuming no wings and things like that are redirecting forces. We're assuming no air resistance. It's 0. It is not going to get any faster left, right. It is not going to get any slower left, right. That is the critical thing here. So, just to clarify this, if I throw it with some initial x velocity of 10 meters per second, its final x velocity will also be 10. Its x. Its y, its up, down will change. It will either be going faster upward, well, it'll be going more down by the end. Its y velocity will change. Its y velocity, so its acceleration on the x is 0. If its initial y velocity was 2 meters per second, it will be at the end, I don't know, maybe it's -3. All that matters is gravity pulls things down. It makes them go faster downwards. So the y will get affected, but the x does not. The x is not affected by gravity. The x is not affected by gravity. That's x and y are separate. Gravity only affects up, down. There's no wings attached to this. There's no air resistance. Wings only work if there's air resistance. You can have wings in space and they do jack squat. Which leads to an interesting thing with Star Wars. In Star Wars, when they're swooping around, it's completely ridiculous because the wings do jack squat in space. They only affect air. There's no air in space. Yeah, Star Wars does a terrible job with how planes would behave in rockets would behave in space, but it's fun to watch and all that. All right, great. Oh, look, it's the same thing I've said 2 times now. Again in all bold, all caps. Gravity is only down. Gravity does not affect anything in the x direction. They are separate. X, y are separate. It sounds, it's like, man, why does he keep yelling this? It's because if you understand this, this will be very straightforward. If you make a mistake here, it's because you'll have forgotten this. It's one idea that's very easy, and it's a really weird idea. You all are used to a world of seeing things where the x and y are stuck together. We're learning how to break them apart because that's the only way you can solve these problems. And you can't see that. You can't see the x and y broken. You all haven't lived a world where you can see an object and see the velocity vectors broken up into their x and y components. So that's why this is a challenge. You're used to a world where they're stuck together, and we have to learn, hey, you can break them apart, and that's actually how we're going to solve these. It's a requirement. All right. Just some random vocab things because these words might get played. You've probably heard most of these, but I just want to make sure we're cool with it. Trajectory is the path it takes. The time of flight is the time it's in the air before, once it leaves the hand to once it, right before it hits something. Remember, the final velocity is not 0. Whenever I toss a ball and say, how fast is it going right before it hits the ground? Or how fast is it going when it hits the ground? It's not 0. It's always right before it hits the ground. That's always whatever. Range is the horizontal. That's delta x. Range is how far you went, delta x. Maximum height is what it sounds like. It's your highest point, how high you are. That isn't necessarily final position, because it could fall after that. But it does correspond to the y position at the highest point. Okay. Great. Good news, now. Now we just do problems. How do we make sense? Now we just apply all this stuff I said. So there's a picture of things. Wow. So this is an example of problems. We're not going to there's nothing to actually solve in this problem. This is just, hey, I launched something. Maybe this problem would say, I launched something with some velocity. How high does it go? And we find that. Or I'd say, what's its range? And we'd find its delta x. Again, just pictures of these problems. These are problems where you want to draw a picture. A picture will help you. If you do not draw a picture, you're more likely to make a mistake, and it's harder to see how to break things into components. You will see what I mean. I always draw a picture for these because you have vectors involved, and you need to draw the direction of them to make your life easier. So, great. Oh, look, split everything into X and Y. The next tip for you all, sorry, I lied. I apologize. Before we actually solve problems, there's one more tip I want to teach you all. We're always going to just assume you're going to find time. I don't care if the problem says find time. Assume you're going to need to find time. Just be prepared for that. 90% of these problems, you're going to need to find time, even if I don't ask for it. Just expect that. Remember, time is the only variable that translates across X and Y. So just assume, even if the problem doesn't say it, find time. You have to decide how to find time. Am I going to do it with the X components or the Y components? And basically you have to say which one's the limiting case. Which one determines my time? Is it how far I go left, right? Or is it how far I go up, down? And that sounds like a complicated thing, but it's literally just, there's a few examples here that make a case point. If you hit a wall, it's your horizontal. Or if I give the horizontal. If I'm 10 meters from a wall and I throw the baseball at it, the baseball will stop when it hits the wall. I don't care how up, down it went. When it hits that wall, and that's a horizontal distance between us. Whereas if I throw a baseball and it hits the ground, it's going to be the Y is going to determine where's its final Y and that kind of thing. So let's just quickly do a couple examples. Darts tossed across a room. Which component determines the time? X or Y? That's the wrong problem. Darts tossed across the room, baseballs tossed across the room, whatever. What determines the time? Is it how far it's traveled left, right, or is it how far it's traveled up, down? What limits the time that it's in the air? Give you all 30 seconds or so to think about this. No math. All right. 10-ish more seconds or something. If you haven't guessed, make your guess. We'll draw a pretty picture of this. Wow, so good. Here's a dart. There's a wall. All right. And 5, 4, 3, 2, 1. Okay, so here's my picture. I put where the person started. I decided to start at the origin. You can decide where that is. Doesn't really matter. They start at 0. The wall is 10 meters away. What's going to determine when this dart stops flying? It's when it's traveled this distance. Horizontally. Doesn't matter how fast. Okay, if you throw it too slow, it's not going to reach the wall. But assuming you throw it hard enough to reach the wall, what's going to determine when it ends its flight? When delta x equals 10 meters. We have no idea where it's going to land, up, down. In fact, there's a problem in the problem set saying, hey, find how far it's going to fall. But if we know it's delta x, we can find the time. And if we find the time, we can put that into the y equations and figure out how far it's going to fall. So that's going to be the trend here, y'all. We have to decide what limits it, find the time based on that, and then figure out whatever else we want to figure out. So the next one, that one goes there. I'm not going to even open this one. I want things to move quickly because I want to get to at least a problem to solve today. All right, cannon shoots Joe Schmo through the air, after which he lands a nice comfy net. Look, I'll open it, and then I'll just start solving it by the time I finish solving it. It's a freebie, right? All right. So, look, here's Joe Schmo. He shoots himself out of a cannon. Whee! And he lands somewhere over here. How do we decide which one limits the time? We think about what we know the final and initial of. We have no idea how far this person went. So sure, x initial equals 0. How exciting. That's where I start. You know what? Y initial equals 0. Why? Because I'm at let's say the ground is 0. I have no idea how far the person went. There's no way from this picture to tell that. But even without knowing that, what's their final Y position? 0. Where do they end up back at? The ground. You have more information in the Y direction, so we're going to use that to find the time. I would have to give you the velocity and the angle to actually solve this. But here I know my initial Y, I know my final Y. That's when does the person stop flying? When they return back to the ground. That's my limiter. That's what's going to determine my time of flight. Does not matter how far they travel left, right. That does not determine their time of flight because we have no idea how far. You have to actually calculate that. So great. Hopefully people have answered. I'll give 20 seconds, I guess. I don't know. There's always a delay on the stream. But that's the idea, y'all. This is how you're going to find the time. This is a strategy that's kind of like behind the scenes that sometimes gets glossed over. So I want to spend some time on it. And now we'll solve problems. So I'll just leave that open. Whatever. I'll close at some point. So great. Look, remember, y'all, Vx is constant. There's no acceleration in the x. I am not going to give you any problems with rockets attached to them. I'm not going to give you any problems with this thing speeding up or slowing down left, right. We're going to keep it simple. But this just shows you, remember I told you on the world you can't see these things split up? This shows you what they look like split up. In the beginning, there's an x component to the right and a y component up. A little bit later, my x component's still to the right, exact same amount, but my y component's a little bit smaller. At the very top, what's my y component of velocity at the top? 0. Do you all remember when we toss the ball straight up? What's its velocity at the highest point? 0 in the y direction. At the highest point, Vy equals 0. But what about my x component? It's still there. It's just all your velocity is just the x component. Here, let me make these different colors. Y component gets smaller and smaller. At the top, it's 0. But notice my x component is always the same. Y component then starts going down. X component, it's the same. The red arrow is the same size everywhere on this picture because there's no acceleration in the x and all that good stuff. Okay. An airplane traveling to the right with a speed of 500 kilometers per hour. Kilometers, hours, guess what that means? You're going to have to convert. At a height of 800 meters, drops a crate of supplies. See the following figure. There isn't one. There is one in the problem set, but you all draw it yourself. And here, you got enough information. If the parachute fails to open, i.e., ignore air resistance, how far in front of the release point, and this is saying how far horizontally, how far in front of the release point does the crate hit the ground? What is my... How far did I move to the right? Draw a picture. If you do not draw a picture, this will be very tricky for you to understand what you're doing and why. So I'll give you all some time and then I will draw the picture. In your picture, put your variables. Put the numbers I gave you. Show what they represent in this picture.
My question is there a right way to see the index here and the angle here or here?
So what side is up? This side. What's that measure?
Meter an hour.
So those are two different ones. So we can't make a triangle with two different units.
Oh, I didn't know that.
Yeah, the triangle has to have all the same units. And it's got to represent the same. It's kind of apples to oranges kind of thing.
Got it. So I'm not doing a triangle.
They're gonna have to use, you know.
Okay.
All right, y'all. So I got a plane. There it is. It's flying horizontally. Which way is that? Up, down, or left, right? Left, right. Pick a direction. It really doesn't matter in this case. Let's say it's going to the right. With some velocity. Is that its beginning velocity or its end velocity? It's its beginning velocity. Is that the x component or the y component? Up, down, or left, right? That is my initial velocity in the x direction. 500 kilometers per hour. If we want, we could do the unit conversion now. That's going to be 500 E3 meters. So I'll write it out. 500, then we're going to multiply. Well, no, I'm just going to 500 E3 divided by 3,600. If you're unsure how to get 60 minutes in an hour, 60 seconds in a minute, make certain you're comfortable with doing this. I'm not writing out as much because we did the practice for this, like I wrote out more previously, but this is one of those skills that you all need to make certain you're comfortable with. 138.89 meters per second. We always check our work. Did my unit conversion make sense? 138 meters per second. That is, if we use that 27 meters per second, that is going about 300 miles per hour. It's a plane. They're allowed to go 300 miles per hour. It's not a person walking. It's not a car driving. If you have a car driving this fast, it's no, not happening. Great. At a height of 800 meters, measured with respect to what? How is height measured? What am I measuring 800 meters with respect to? I should draw the ground. That might be helpful. Because if I don't have a reference, this is 800 meters up. What variable corresponds to 800 meters vertical? Y. Initial or final? Initial. It starts here. Again, the more you write this stuff out, we're going to do it in our givens as well, but I like to put it in my picture. Because if you don't understand, the picture makes it easier to identify the variables. Without the picture, it might be tricky to realize, is this X? Is this Y? Pictures help you visualize it and play the matching game. Great. So, I got a crate in this box, in this thing. I drew the plane. If the plane's going this fast, how fast is the crate going? Exact same. Exact same. That's why I said it's the initial. Great. That's the initial. Where is this thing going to end up at? The ground. So it's going to go doot, 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 doot. And it's going to end up on the ground. Great. What do we know about it when it hits? What that tells us some givens. When it's at the ground, what do we know? We know the Y final. Y'all tell me, based on this picture, what is its final Y position? 0. The pictures are nice. Without the picture, this might be tricky to figure out. As you do more of these, it gets easier and easier. Questions? Reminder to you all. Yes, it will hit the ground. No, the Y velocity is not 0 at the end. The final Y velocity is not 0. That is a trap that a lot of people fall into because, again, you're used to the world. You're like, oh, things hit the ground, they stop. Yes, that is true. You cannot do the math involved with it hitting the ground. There is not enough information. We always consider right before it. I know it says hit the ground here, but you in your head have to realize that means right before it hits the ground. Because obviously when it hits the ground, it will stop eventually. But how is it going to stop? Is it going to bounce, slide, explode into a million pieces? Like you can see the ambiguity there. That's a problem NASA has to figure out whenever they land on a planet. How are we going to land? And that's a complex problem. Sometimes they do just literally have the payload slam into the surface. Other times they have a rocket on it or a parachute, whatever. We're not worried about this box surviving. We're not worried about how it's hitting the ground. We just want to know how far it went, i.e. right before it hit the ground. Okay. So let's make our nice little list of givens. I'm just going to take the ones from the picture. We know our initial velocity in the x direction. And actually, I'm going to start using a skill that I saw other people use in the past, and I think this is great. When you are doing x and y coordinates, you can do this beautiful table, x and y. And you can and this, I guess, gets a little funky. How do they do? They have like velocity. I've seen people do this, like a velocity initial, velocity final, acceleration. I've seen people do this. I guess you could do like x initial, x final, which looks a little weird because there's an x and y. I've seen people do this, and I think it's a great way to organize information. You make a little table. It splits things into x and y. That's totally valid. I'm going to do it both ways, the way I do it, and neither way is better than the other. You pick whatever fits your... I just kind of write them over here. I mean, I kind of already did. So what's my initial velocity in the x direction? I did not leave myself enough room. Line. My initial velocity was 138.89. Do we know the initial velocity in the y direction? Do we know how fast it's going up, down in the beginning? Check out your picture and you tell me. How fast is it going up, down in the beginning? 0. At no point in the problem does it say it's going up or down in the beginning. According to our picture, it's just going horizontal. If it's just going horizontal, my initial velocity in the y direction is 0. So again, I'm going to write these kind of over here because this is how I tend to do it, but it's the exact same thing. These two lists are the exact same lists. The initial y is 0. Because in the beginning, it's not going up or down at all. It is not moving up. It is not moving down. It's only moving left, right. All right, you all try to fill out the rest. I don't want to give away too much. There is a lot of variables here. See if you can fill in that table. You can fill in almost all of it. Yeah, you can fill in all of it except 2 boxes. Yeah. You can fill it all in except 2 boxes. And our only goal today is we're going to step 1 and step 2. We'll leave the rest of solving it to next time. I only want so much in your all's heads. Doing steps 1 and 2 is sufficient. Yeah, so we converted from hours to seconds to 60-60. Yep. Yeah. It's a good question.
So, the final velocity in the y direction is not.
There is one more.
Right before it hits, so you have some speed in the y direction.
And we can just go one by one.
After you know the velocity. Final y position. Always double check. That'll if it's 0 meters, 0 meters per second, that's a lot. You have 0 meters, you have 0 meters. The initial y.
So then the last one, do we know the minus position or the vertical? Where is my initial position? Where do I set it?
So I will say, if you're not given the coordinate system, you can always make.
What do you measure with respect to? Where's your 0 point? Where does that correspond?
Yeah, it's always one zero starting.
You can decide. I don't care.
So where do you want?
You want to start at 0 and perfect. All right. Yeah, final position. It ends at 0.
If you're setting the ground is 0 by.
It's delta 1.
Is negative. X initial. Say X initial is equal to 0. Where the plane starts. Y is 0.
To give you all a checkpoint, I'm going to highlight the 2 boxes you don't know. You do not know the final and the y, and you do not know how far you traveled horizontally. Those are the only 2 you don't know. Everything else you can figure out. Everything else is a given, as in no math required.
Yeah, X initial.
Oh, you're right.
Okay, we're interested in that's after it's done some interaction with the ground, like down to acceleration.
What's your acceleration index?
So just at the instant
I'm not speeding up or slowing down. Your velocity stays the same.
So would we do negative 130?
That's the exact same number.
Oh, is
If it doesn't speed up or slow down. And that's always going to be true in these problems, that the x velocity is always going to stay the same the entire time.
Oh, wait, so it wouldn't be 0.
No. 0 would make it slow down.
Oh, wait.
Yep.
No, I knew that.
All right, so let's do the acceleration one because we practiced that before. What's my acceleration in the x? Left, right? 0 meters per second squared. What's my acceleration in the y? Negative 9.8. If my acceleration in the x is 0, does that mean I'm speeding up, slowing down, or staying the same? So my initial and my final in the x are identical. This is always going to be true in every single projectile motion problem you do. In the x direction, the velocity doesn't change because why should it? Nothing is making it go faster or slower left, right. There is no air resistance or anything else. All right, great. What's my initial position in the x? You actually get to decide this. Pick a number. It doesn't matter. 0 is a great number to pick for where you start. You could pick any number in this problem and it would be fine. At this point, we're trying to say how far does it travel. So it actually, I could pick my initial position as 100, 200, 300. You'll see what I mean in a second. What's my initial position in the y? How far up do I start? 800. We're deciding that the ground is 0, which says, where does my crate end up? At 0. The y final position is 0. Now, step 2, and this is where I told you all, it doesn't matter what your initial position is, because what we're solving for here, it's not technically x final, it's delta x. Now, if you chose x initial to be 0, then you just solve for xf, and that works out great. It is generally a smart idea to make your beginning or your end 0. Choose a reference point that makes your math easier, i.e. either start at 0 or end at 0, horizontally and vertically. You're allowed to choose. There's no rules against this. All right. Again, at this point, y'all, this is good enough. If you can do this, this is the hard part of the problem. The kinematics, the plugging, the choosing the equations, you will find that that is the simple part. This is where the mistakes will happen. Or if you put x variables and y equations and things like that. So next class, we'll actually do the equations. We are at a comfy place right now because we got like an hour 20 next class just to do 2D kinematics problems before we do our lab, which shock and awe will be 2D kinematics. It'll be throwing a ball. So, have a good one, y'all. Practice your kinematics. It's a good time. So much fun. Sure.